Hi everyone, welcome back. Hope you all are doing well. So today we're doing May June 2017, paper 129701 chemistry. So let's start. Okay, question number 1. In which species are the numbers of protons, neutrons and electrons all different? Okay, so this is 199 F minus. Obviously it has 9 protons and because it has a negative charge that means it has one more electron than the number of protons, so it has 10 electrons, and the number of neutrons will be 19 minus 9, so that's 10 as well. But then they're not all different because the number of neutrons and the number of electrons are the same, right? So A cannot be the answer. Then B, we have 2311 Na plus, so the number of protons is 11, and then because it has a positive charge, so it has one more proton than electrons, so it has 10 electrons then, right? It's lost one electron. And then the number of neutrons will be 23 minus 11, so it's just 12 neutrons. And 11, 10, and 12 are all different. So then that means that B would probably be the correct answer because these are all different numbers. But we'll check the other options as well. So 3115p, so it has 15 protons, and then because it's neutral, so it has the same number of electrons, 15 electrons, and again we can immediately cross it out for that reason. But anyways, then the neutron number would be 31 minus 15, which is 16 neutrons. And then for 3216 S2 minus, you have 16 protons, and because it has a 2 negative charge, it has 2 more electrons than protons, so it will have 18 electrons, and then the neutrons will be 32 minus 16, so 16 neutrons. Okay, so yeah, again 16 protons, 16 neutrons, so D is also wrong, and so the only correct answer possible is B, right? And next question, which would contain 9.03 into 10 to the power of 23 oxygen atoms. Okay, so we have 0.25 moles of aluminium oxide. So aluminium oxide is Al2O3, right? So if we have like for 1 mole of aluminium oxide, we have 3 atoms of oxygen, right? So it means that for every 1 mole of aluminium oxide, we have basically 3 moles of oxygen atoms, right? Because it has like each like molecule of Al2O3 has what do you call it? 3 atoms of oxygen, right? For each formula unit of Al2O3. But the point is that like yeah, so if we it's 0.25 moles of aluminium oxide, so it will be 0.25 because it is an ionic compound, right? But just with some covalent character. So I guess it's a formula unit sounds better. And you guys 0.25. So the number of moles of oxygen atoms would basically be 0.25 into 3 then, right? So 0.25 into 3, and then you times that by like because you have to find the number of atoms, not the number of moles. So you multiply this by the number of moles of oxygen atoms. You multiply it by Avogadro's constant to get the number of oxygen atoms. Okay, so it's times 6.022 into 10 to the power of 23. So what do you get? You get 4.5165 into 10 to the power of 23 um, atoms of oxygen. Okay, 4.5165 into 10 to the power of 23. So obviously that's not 9.03 into 10 to the power of 23. So you can cross this out. Okay. Next, you will see the next option, which is 0.75 moles of sulfur dioxide. So sulfur dioxide is SO2. So for every 1 molecule of SO2, we have 2 moles of oxygen, right? So atoms, oxygen atoms in that. So that means that the number of moles of oxygen atoms is 0.75 into 2 because there are 0.75 moles of SO2. So that means the moles of oxygen atoms will be 0.75 into 2. So the number of oxygen atoms will be 0.75 into 2 into 6.022 into 10 to the power of 23. So to do this calculation, and we get 9.033 into 10 to the power of 23. which is like, to three significant figures, it would be 9.03 to 10 power 23 oxygen atoms. So that means that B is probably the answer, because 9.03 to 10 power 20, that's what we got. But we can try out the other options as well. So we have sulfur trioxide, which is SO3. Now here we have 1.5 moles of sulfur trioxide, so the number of moles of oxygen atoms will be 1.5 into 3, right? And the number of oxygen atoms, I mean, would be, the number of moles of oxygen atoms times Avogadro's constant again. So 1.5 into 3 into 6.02 to the 10 to the power 23. So that is 2.7099 into 10 to the power of 24 atoms, okay, of oxygen, which is again obviously not the correct answer. And then we have moles of water as well, 3 moles of water. So 3.0. So that means, like, for every 1 mole of water, we have one mole of oxygen atoms, right? So that means you just do 3.0 times 1, basically, or just keep it as 3.0, it's fine. And then times that by, multiply that by 6.022 into 10 to the power of 23. So we get 1.8066 into 10 to the power of 24 atoms of oxygen, which is again not the correct answer, right? So obviously, because we all got all the other options as wrong, so B is going to be the correct answer. So we got 9.033 into 10 to the power of 23 oxygen atoms for. So yeah. Next question. In some fireworks, there is a reaction between powdered aluminium and powdered barium nitrate. Heat is evolved and unreactive gas is produced. So an unreactive gas is produced and all nitrogen atoms are reduced. Okay. So heat is evolved as well, so it's probably some type of reaction, right? But an unreactive gas is produced. If you look at the options, we have in first one, like in option A, we have nitrogen monoxide produced. In option B, you have oxygen produced. In option C and in option D, you have nitrogen produced. So nitrogen is unreactive, right? Because of that very strong triple bond between the two nitrogen atoms. It's inert. And but as for oxygen is highly reactive, right? It's a very reactive species, right? I mean, yeah, we use it for combusting things and stuff. And uh, nitrogen monoxide is also a very, it's highly reactive as well. Um, if you can draw it out as well, like it's kind of like this, two lone pairs here, and then we have two like a double bond there. There are other ways to draw it as well, I think, but you know, basically it has this unpaired electron, right? In nitrogen monoxide, you have that unpaired electron, so it's a highly reactive free radical species, from what I know. So yeah, and oxygen is obviously also a highly reactive species. Then nitrogen is unreactive, it's non-polar and it's inert and stuff. So yeah, so that means basically that because they said an unreactive gas is produced, we can immediately cross out options A and B because those don't give you unreactive gases, right? But C and D do give you unreactive gases, so it's basically now we have to see which one is balanced, I guess. So let's see. Okay, so 10, like I'm checking option C now. So 10 Al, 5 times 2 is 10. So aluminium is balanced, okay. And then we have 3 Ba. So barium is also balanced. And then we have, like on the right hand side, we have 3 moles of N2, so that's 3 times 2, 6. So 6 nitrogens on the right side. On the left side, we have N, like 2 atoms of N, and then multiply that by 3 as well, because that's the stoichiometric coefficient. So that also gives you like 2 times 3 is 6. So you also have 6 um, N atoms on the left side. So 6 equals to 6. So then we have to check oxygen as well. So on the left side, we have 3 times 2, that's 6. Then 6 times 3 is 18. So we have 18 oxygen atoms on the left side. And on the right side, we have 5 times 3 is 15. So 15. And then in barium oxide, we have 3 more oxygen atoms. So 15 plus 3 is also 18. So the oxygen atoms are also balanced. So all of the species, like all of the atoms and stuff, seem to be balanced. So, and the charges, like as well, there's no, charges, overall charges on the left or right hand side. So it seems to be a balanced equation as well. So I would say C is the correct answer, but again, we should check the, what do you call it, check D as well. So there's 10 Al, and on this side we have 10 Al as well. Then 18Ba on the right hand side, we also have 18Ba, so barium and aluminum are balanced. Then on the left side, we have 2N, but then like over here, it's like N2, right? So 2N times 18, so that means 36 atoms of nitrogen basically. And then on the right side, right hand side, we have N like 3N times 10 because the stoichiometric coefficient is 10, so 3 times 10. And then over here we also have 3 N2, so that 3 times 2 is 6, so we have 6 more. So it becomes 30 plus 6, so that's 36 atoms of nitrogen, so that's also balanced. But if you look at oxygen, okay, this is weird. Like, okay, well, till now everything has been balanced. I don't know about oxygen. Let's check, I suppose. So on the left side, we have 3 times 2, 6, 6 times 18. So 6 times 18 is 108. Okay. So it's 108 oxygen atoms on the left side. And on the right hand side, we have 3 times 3, that's 9. And 9 times 10 is 90. So 90, and then we have 18 more oxygen atoms from BaO. So 90 plus 18 is also 108. Wow. Okay. So that means that they're both balanced. Okay, so we can't compare on the basis of balancing. Let me read the question more carefully. So heat is evolved, okay, and all nitrogen atoms are reduced. Maybe it's something to do with that. So over here in barium nitrate, let me see. So barium nitrate, you have Ba2 plus and NO3 minus ions, right? So in NO3 minus, your you have the oxygen has a fixed oxidation state of -2, right? Usually, and there are three oxygen atoms. We multiply that by 3. Let's take the oxidation number of nitrogen as X, and then because the whole charge of this NO3 minus anion is -1, so I'm going to put this equal to -1, right? So X equals to -1 plus 6. I'm trying to find the oxidation number of nitrogen here. So X equals to plus 5, right? So in barium nitrate, it's plus 5. Okay, the oxidation state of nitrogen. So now let's look at the right hand side. Okay, on the right hand side, we have N2, which is obviously because it's the how nitrogen exists naturally like N2, so that's the oxidation number is going to be 0 there. Even in option D, that's the case. But so basically plus 5 to 0 is definitely like you're decreasing, your oxidation number is decreasing, so it's definitely a reduction. So in option C, nitrogen is definitely being reduced, and even here in option D, in this part, nitrogen is definitely being reduced. But if you look at this one, in NO, like AlNO3 thrice. So that's between, like, we have the ions Al3 plus and NO3 minus, right? So over here NO3 minus, we also have NO3 minus in this, like AlNO3 thrice also has NO3 minus, right? So in NO3 minus you have your nitrogen atoms as plus 5, right? So you have basically in total you have like um how many, like 2 times 18, so that's 36 nitrogen atoms, right? And over here you have 30 of them, like 3 times 10, so 30 of the nitrogen atoms are remaining as plus 5, but then only 6 of them are being reduced to N2, right? So the thing is, the question said that all nitrogen atoms are reduced, right? But that's not the case in D, because in D you have AlNO3 thrice, where it's just like, you had plus 5 in the reactants, and 30 of your nitrogen atoms for option D, 30 for nitrogen atoms are remaining as plus 5 instead of going to 0 oxidation state, right? So you don't have like reduction of all the nitrogen atoms. So because of that, I think option D is wrong, because not all the nitrogen atoms are reduced in option D. So therefore, the answer must be C, where there is definitely an unreactive gas produced and all nitrogen atoms are reduced as well. And yeah, heat must be evolved as well. So yeah, C is going to be the answer. Okay. Okay, next question. Which organic compound has the highest boiling point? So we have C, CH3, 4, and we have CH3, CH2, 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 CH3. Okay. And then we have CH3CO, CH2, CH3, then CH3, CH, OH, CH2, CH3. Okay. So in these two, like their, like basically the boiling point would depend on the strength of the intramolecular forces, right? So in option A and B, we just have temporary dipole induced dipole forces, or just you could say like we call it London dispersion forces, right? So those are the only intermolecular forces you have. So, because they are non-polar molecules, right? So yeah, they just have London dispersion forces. So that means they don't really have very high boiling points. But if you look at option C, you have, let me draw it out, CH3, CO, CH2, CH3, right? So here you have a highly electronegative oxygen atom. Like the five most electronegative atoms are fluorine, oxygen, nitrogen, chlorine, and bromine, right? So you have oxygen and carbon. They have a quite a like they have quite a significant electronegativity difference. Okay, so this carbon is partially positive, this oxygen is partially negative, and there's basically permanent dipole forces in this. Okay, permanent dipole forces in CH3CO, CH2, CH3, and so basic, and also obviously because it does have permanent dipole and London dispersion forces, right? So, but its most significant force would be permanent dipole forces. So because of that, has a higher boiling point than CAC, CH3, 4, or CH3, CH2, 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 CH3. So you can eliminate options A and B because C definitely has the higher boiling point compared to A and B. But then if you look at option B, CH3, CHOH, CH2, CH2. So again, let me just draw that out. CH3, CH. Okay, that doesn't look like a very good drawing. Wait, CH, just H down here, OH here, and then CH2, CH3. So this one actually has hydrogen bonding as its most significant intermolecular force. Like obviously, it also has permanent dipole forces and temporary dipole or London dispersion forces, but it has hydrogen bonding as its most significant force. So it has it because of that, because hydrogen bonding is the strongest intermolecular force out of London dispersion forces and permanent dipole forces and hydrogen bonding. So hydrogen bonding is the strongest one. So therefore, um, this compound CH3, CHOH, CH2, CH3 would have the highest boiling point if you compare all of these options. So because hydrogen bonding basically exists in those covalent compounds where you have one of the like three most electronegative elements, right? Fluorine, oxygen, or nitrogen that is bonded to hydrogen, which is the case here. Like if you look at this OH, so obviously when you have an alcohol or a carboxylic acid, you would have hydrogen bonding. You predict that, as well as in compound like ammonia, for example, because that's NH3, so NH3, right? So yeah, but because of that hydrogen bonding, which is strongest intermolecular force out of temporary dipole forces and permanent dipole forces and hydrogen bonding, so it's the strongest one out of those three. So because of that, D has the highest boiling point because it has hydrogen bonding, whereas C only has, where C does not have hydrogen bonding, it has permanent dipole and London dispersion forces, and then A and B only have London dispersion forces, whereas D has, hydrogen bonding and permanent dipole forces, and hydrogen bonding is very, very strong. So yeah, and so the answer is going to be D. Next question. At a temperature of 2500 kelvins and a pressure of 1.00 into 10 to the power of negative 4 pascals, a sample of 0.321 grams of sulfur vapor has a volume of 2.08 into 10 to the power of 6 cubic meters. What is the molecular formula of sulfur under these conditions? Okay, so we just have to use the formula PV equals to nRT because they gave us the mass, and like, so I can just like instead of n, I will use the fact that we know that n equals m over mr, so n equals the mass, and the moles equals mass over molar mass, right? So I'll just substitute that in, so m over mr into RT. Okay, that doesn't actually look like MR. Let me write it better. Okay, so now we don't know the MR, right? And like to find out the molecular formula, I will first determine the MR because I know everything else. So MR equals to MRT over PV. Okay, so I'll just substitute the values in. So mass is 0.321 of that sulfur vapor, and the ideal gas constant is 8.31. Temperature is 2500 Kelvin. This already in Kelvin, so no need to convert stuff. And then, oh, this line is not, let me just erase that and make a better line. Okay, And the pressure is 1.00 into 10 to the power of negative 4 pascals. Then the volume is 2.08 into 10 to the power of 6 cubic meters. So already in meters cubed, so I don't need to convert it into anything more, because it should be in meters cubed for this equation. Okay, so now just do this calculation on your calculators. 2500, and then divide that by 10 to the negative 4 into 2.08 into 10 to the power of 6. So you get 32.061418 grams per mole. So, if you check the periodic table, here you can see sulfur has a relative atomic mass of 32.1, right? So I also got an answer that is approximately 32.1 grams per mole. So because of that, means that the molecular formula of sulfur in these conditions is just S, because S has a relative atomic mass of 32.1, right? So that's why my answer is going to be A, because that's what I got from the calculation as well. Okay, so yeah, it just existed S. If it was S2, then you would get the answer for the MR as 32.1 into 2, which is 64.2. And if it was S4, then it would be 32.1 into 4, which is 128.4. If it was S8, then it would be 32.1 into 8, which is 56.8. So yeah, that is the logic. And next question now. Which reaction involves a decrease in the bond angle at a carbon atom? Okay, so you have bromoethane. Bromoethane would be CCH, H, 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 and you reflux it with ethanolic sodium hydroxide. So ethanolic sodium hydroxide. Ethanolic sodium hydroxide means that it's an elimination reaction, right? So we would get an alkene out of this. So it would become C double one C. So basically, bromoethane will turn into ethene, and so HBr is eliminated basically, right? So yeah, or actually NABR, because that, I mean, you get HBr. HBr. There's a better way to do this. I could just write down NaOH and see which product you get. Yeah, just guessing it. NaOH plus CH3CH2. Yeah, okay, so you get ethene firstly, CH2CH2 plus, okay, so you have Na and then, yep, yeah, I think it would be NaBr, and then the other H from this atom would combine with the OH, so it becomes H2O. So that makes more sense, right? Yeah, that makes more sense. So then that's not the question anyways, but those main products form. But then here, because you have this carbon is bonded, like this carbon or even this carbon, both of them are bonded to four groups. So basically four sigma bonds are formed by each carbon atom. So that means that the bond angle is 109.5 degrees, so like tetrahedral geometry around each carbon atom. So 109.5 degree bond angle. Okay, and then for ethanolic sodium hydroxide, on the other hand, this carbon forms three sigma bonds and no lone pairs, obviously. And this carbon as well forms three sigma bonds and no lone pairs, and there's one pi bond as well. If you don't count, then we're counting the steric number. So three sigma bonds means, and no lone pairs means that it's 120-degree bond angle. So it's trigonoplanar geometry around each carbon atom, right? So 109.5 degrees to 120 degrees is an increase in bond angle, right? Not a decrease. So that's why A cannot be the answer. Now, if you look at option B, we have the complete combustion of methane in air. It's not taking, okay. And that would be, methane is CH4, right? So CH4 plus O2 gives you CO2 plus H2. Let me draw it out fully actually. OCO. And then you have CH, H, 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 right? Oh, it's not pretty balanced, is it? So we have let's see how to balance it, because we have four hydrogen atoms here, so we make this 2H2, and 2 plus 2 is 4, so we make this 2O2. So does that seem balanced? 2 2s are 4, 2 plus 2 4, so 4. Yeah, it seems balanced to me, but again, if I made a mistake, tell me in the comments. And okay, so over here, carbon is like it has four sigma bonds. One sigma bond, two second one, third one, fourth one. So four sigma bonds and no lone pairs. So it has a tetrahedral geometry at 109.5 degrees bond angle, and in methane, so 109.5 degrees. And then in CO2, it is, you have two sigma bonds, and again carbon is forming four bonds, two sigma bonds, and then there are two pi bonds as well. Pi bonds are not counted in the steric number. There are no lone pairs. The steric number is basically because there are two sigma bonds and no lone pairs, so it's just two. And because of that, this is just linear geometry, and linear geometry means 180 degrees bond angle, right? So from 109.5 degrees, it's going to 180 degrees in carbon dioxide. So again, that's an increase in bond angle, not a decrease. That's why B cannot be the answer either. And option C, um, ethanol heated with concentrated H2SO4. So that's a dehydration reaction, right? Like an elimination of water. So ethanol is CH3, CH2, OH, right? And you're heating it with concentrated H2SO4, so you get CH3, or in fact, that you lose this OH, and then from the adjacent carbon atom to this one, lose the H, so you get CH double bond, CH. So you get CH, you get again ethene. So yeah, you get ethene. We draw it like this, okay. And then obviously you get water eliminated from that, right? So here in this one, you have both the carbon atoms, like they have four sigma bonds, no lone pairs, that's 109.5 degrees bond angle. And then here you have like both of the carbon atoms form three sigma bonds, there's one pi bond, so you don't count that in the steric number, which is the number of lone pairs plus sigma bonds. But you have three sigma bonds, no lone pairs, right? So that means it's 100 and, the bond angle is 120 degrees, planar geometry. And so 109.5 degrees to 120 degrees is again an increase in bond angle, not a decrease. So C cannot be the answer. Therefore, since A, B, and C are all wrong, D must be the answer. But again, we should confirm it by drawing it. So I will erase the first one, so I have some space to do this. Okay. So then we have polymerization of ethene, right? So we have C double bond, C. Wait, yeah, that's ethene. And then when it's polymerized, we get C, C, H, 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 and H. Okay, just repeat it n times. Okay, so here we have 120 degrees bond angle, right? Because each carbon has like forms three sigma bonds, and there's one pi bond which you don't count, but three sigma bonds and no lone pairs, which means 120-degree bond angle, signal panel geometry, right, around each carbon atom. And then here in polyethene, you have like, each carbon atom is forming four sigma bonds, no lone pairs. Four sigma bonds and no lone pairs means it's around each carbon atom there's tetrahedral geometry and it's 109.5 degree bond angle, right? So from 120 degrees we are going to 109.5 degrees, which is a decrease in bond angle, right? And since this is a decrease in bond angle, that's what the question was asking for. So that means D is the correct answer, right? So yeah, D is the correct option. And now we will go to question number 7. In the high temperatures of car engines, nitrogen, that's nitrogen. I drew stuff so it doesn't look like nitrogen, but nitrogen, yeah, nitrogen reacts with oxygen to give nitrogen monoxide. Okay, and then we can see that the delta H given is plus 90 kilojoules per mole, right? So that's, it's an endothermic reaction. So this reaction has activation energy EA. Which reaction pathway diagram could correctly represent this reaction? Okay, so since it's an endothermic reaction, the delta H arrow should be upwards, not downwards, because if it was downwards, then that would be an exothermic reaction. So first let me check if the delta H arrow is upwards, and that seems to be the case in all four of the options. Then the delta H arrow should be from the reactants to the product. So let me see if that's the case for all of them. So it should be from the reactants to the products, which is not the case in option A. It's actually going from the product. I mean, it's upwards, yes, but it's going from the products to the reactants. So that means A is wrong, basically. It should be the delta H arrow should be from the reactants to the products. And in B, it's going from N2 plus half N2 plus half O2 to NO. So that's going from the reactants to the product. So B could be possibly, it could possibly be the correct answer. Now let's look at option C and D. Option C, we again have delta H going from the reactants to the products, right? Just like in B. So C could also possibly be the answer. And then in D, again the delta H has arrows going from the reactants to the products. So D could also possibly be the answer. So for now, we've just eliminated A. Now the reaction has activation energy EA. So activation energy should be from the reactants to the peak, right? So like in A, it's correct because it's going from the reactants to the peak. But we already eliminated A based on delta H not being from the reactants to the product. So A is out of the question anyways, but I'm just giving you this EA arrow for A is correct. Okay. Then for B, the activation energy arrow is wrong because it's going from the products to the peak. It should be from the reactants to the peak. So it should be like this, right? So B is wrong for that reason. Now if you look at C has the EA arrow from the reactants to the peak, so C seems to be the correct answer because both the delta H arrows and the activation energy arrows are placed correctly. D has the activation energy going from the peak to the reactants, like it's downwards, but that's wrong because activation energy is a process that like you need to supply energy, right? Like it's an endothermic thing, like the system absorbs energy basically. So it should not be going downwards. Activation energy is the energy required for the reactor. So basically D is wrong. The minimum energy required to start the reaction. So yeah, C is going to be the correct answer for that reason because A, B, and D are wrong. And now we will go to the next question. A reaction sequence is shown. In each stage of this sequence, the sulfur is oxidized, reduced, or neither oxidized nor reduced. Which row is correct? Okay, so let's see. Over here we have oxygen. Oxygen is a fixed oxidation state of -2 usually. So in sulfur dioxide you have two atoms of oxygen, so we have to -2 times 2. Let's take the oxidation state of sulfur as X, and then because SO2 has no overall charge, right? So it's like let's equate this to 0 then, and so X equals to +4. So over here sulfur must have oh no, my laptop is stuck. Wait. Okay. So sulfur must be +4 here. Okay, its oxidation state must be +4. And then in SO3, you have again the oxidation state of oxygen will be -2. There are three oxygen atoms, and that becomes -2 times 3, which is -6. To balance that, because the overall charge of SO3 is 0, so then overall oxidation state of SO3 is 0. So then because of that, sulfur must have an oxidation state of +6. Okay, and in H2SO4 we have two H plus and SO4 2 minus, right? So if I consider just SO4 2 minus, and sulfur I'm taking as X, and then oxygen again will have a fixed oxidation state of -2. There are four oxygen atoms, so I multiply this by 4, and then because the SO4 2 minus ion has an overall charge of -2, so I will equate this to -2. Okay, so then X equals to -2 plus 8. X is equals to +6. So over here in SO4 2 minus, or H2SO4, the oxidation number of sulfur is +6. Okay, so yeah, it's +6. Then in H2S, what do you call it? Hydrogen has a fixed oxidation state of +1. And again, you could have calculated the H2SO4 using that logic too. Like hydrogen has a fixed oxidation state of +1. There are two hydrogen atoms, and then let's take sulfur as X, and then oxygen is -2, right? So -2 times 4 because there are four oxygen atoms. That brings H2SO4 right now, by the way. So X that all equals to 0 because H2SO4 has no overall charge, right? Then +8 -2 will again be +6. You could have used this logic in H2SO4 as well, but anyways, for H2S, again, hydrogen has a fixed oxidation state of +1. There are two hydrogen atoms, so +1 times 2. And then X, we take H2S as X, so that will become plus X equals to 0. So X is equals to -2. So here in H2S, we have sulfur as -2 oxidation state. Then in SO2, again, it's the same thing that we had in the beginning, right? SO2. So if that was +4 there, it's going to be +4 here as well. So yeah, and then we just have to see now whether the changes are oxidation or reduction. So in stage 1 is going from +4 to +6, right? +4 to +6 is an increase in oxidation number. If it's an increase in oxidation number, it's going to be oxidation. So it's either B, C, or D. We can already eliminate option A. Then in from in stage 2 it's going from +6 to +6, which is no change really. So it's neither oxidation nor reduction, so I'm just going to write it as neither. And so then it's going to be either option B or option C now, right? And then in stage 3 it's going from +6 to -2, which is again a decrease in oxidation state. So it's because it's a decrease in oxidation state, it's reduction. And so we get, again, it's either B or C. And then um, in stage 4, it's going from -2 to +4. -2 to +4 means it's an increase in oxidation state. Because it's an increase in oxidation state, that means it's oxidation. And so we get the answer as C, okay, because that's where I have 4 ticks. So yeah, C is the answer. Now, next question. Hydrogen and carbon dioxide gases are mixed at 800 kelvins. Okay, a reversible reaction takes place. At equilibrium, the partial pressures of H2 and CO2 are both 10.0 kilopascals. Let me write this as 10.0 kilopascals. This is also 10.0 kilopascals. Kp is 0.288 at 800 kelvins. Okay, and we do not know what the partial pressure of CO is in the equilibrium mixture. That's what they're asking. What is the partial pressure of CO in the equilibrium mixture? So let me take the partial pressure of CO at 800 kelvins as X. And because H2O and CO, they're both products and they have a 1:1 ratio. So if this is X, like CO's partial pressure is X, then the partial pressure of H2O will also be X. They're all gaseous, so they will all be included in the expression and stuff. Anyways, yeah. So I'll write the Kp expression first. So Kp equals to partial pressure of H2O. Now they're all 1 mole as well, so you don't need to worry about coefficients or anything, right? So yeah, just P H2O times the partial pressure of CO, so partial pressure of the product, right? And then for the reactants, we have partial pressure of H2, that's going to be a new denominator, times the partial pressure of CO2. So that's the expression for Kp. Then I'll substitute the value, so 0.288 equals to, now I had this is X and this is X as well. So X times X over 10.0 times 10.0. So this will become x squared, like you can cross multiply, so of x squared equals 0.288 into 100, right? So x equals to, where's my calculator? So we have to do root of 28.8, right? So let me do that, and that would be 5.36656 kilopascals, which is approximately 5.37 kilopascals correct to 3 significant figures, which corresponds to option A. So option A must be the correct answer. Okay. And again, they already gave, like in the question, they gave you the values of kilopascals, like 10 kilopascals. So that's why I didn't convert anything. And even in the answers, they're asking you for kilopascals, so it should be fine, really. Okay. And yeah, next question. A reaction involved in the contact process is shown. 2SO2 plus O2 gives 2SO3. And delta H is minus 197, so that's an exothermic reaction. Now, the reaction is investigated at 200 kilopascals and 700 kelvins, and the value of the equilibrium constant Kp is found to be Y. Okay. Reaction is then investigated at 1000 kilopascals and 700 kelvins, and the value of Kp is found to be Z. Okay. So, they just measured the Kp at both values, and note that they increased the pressure, but they kept the temperature the same, right? So, really, because the temperature is constant, because the only factor that really changes the value of an equilibrium constant is temperature usually. So um because the temperature is the same, like 700 kelvin, 700 kelvin, so basically the value of the partial the sorry the Kp should be the same um at for both Y and for Z. Like the value of Y and Z should be the same because they're the same temperature, right? Even though the pressure is changing, like the pressure changes, that means that, like is still Kp will remain the same because Kp is only affected by temperature. Even Kc is only affected by temperature. Like equilibrium constants in general are usually only affected by temperature change, right? So then, because of that, because the temperature is the same, so the value of Y and the value of Z should be the same. So B is wrong, C is wrong, D is wrong, A is going to be the right answer because Y and Z are the same. All right, and for the next question. The Boltzmann distribution for the hydrogenation of an alkene at a particular temperature in the absence of a catalyst is shown. Okay, now which row correctly describes the effects of adding nickel to the reaction vessel? So nickel is basically a catalyst, right? And in hydrogenation, yeah, we use hydrogen use nickel catalyst. So then, what are they saying? The shape of the Boltzmann distribution. Well, if you're just adding a catalyst, you're not changing the temperature or anything. The shape of the Boltzmann distribution should not change. Like it stays the same shape. It doesn't change in any way. Like the shape remains the same of the Boltzmann distribution curve. But then the activation energy will shift to the left because the catalyst has been added, right? So because of that catalyst, the um, minimum like energy required to start the reaction, the activation energy that is will become less. So the threshold for the reaction to start is less now. So the activation energy basically will decrease. Is my point. It's to the left on the x-axis, right? So there are more molecules that have energy greater than or equal to the activation energy now. Like this area here, it's greater. Whereas before it was just this much. Now it's that blue one. So there are more molecules that have energy greater than or equal to the activation energy. So there's a greater frequency of collisions that are, they have frequency of collisions. So successful collisions. Anyways, I have two ticks and on C. So C is going to be my answer. Then next question is question number 12. The elements magnesium and sulfur each form doubly charged ions. So how do the atomic radii and ionic radii of these elements compare? So what is period 3? It's sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, right? So we're doing a case study on magnesium and sulfur right now. So they're talking about Mg2 plus and S2 minus later, right? The atomic radii, which is here, and the ionic radii, which is here, right? So across a period, what happens to the atomic radius, or the number of shells remains the same, right? Like across a period, number of shells remains the same. So basically here it is sodium, magnesium, aluminum. This period, this is period one. This is period one. This is period two. This is period three. So this is period three that they're all in, and because of that, they're going to have three shells, right? And number of shells remains the same. Both magnesium and sulfur atoms have the same number of shells, but thing is that the proton numbers increasing. Like magnesium has only 12 protons, whereas sulfur it has 16 protons, right? So because sulfur has more protons, it has a greater nuclear charge, and because of that, the nuclear force of attraction on the valence electrons is greater in sulfur as compared to in magnesium, right? Even though their shielding effect would be fairly the same because they have the same number of shells, fairly almost the same. I mean, the proton number is the more significant thing to consider. For, the nuclear charge increases, and because of that, the atomic radius decreases slightly across a period. Okay, so atomic radius decreases slightly across a period, and because of that, atomic radius decreases slightly. Wait, that's not even the question they're asking. Now that I think about it, because they're not comparing magnesium and sulfur per se. They're comparing magnesium to Mg2 plus and sulfur to S2 minus. But let's look at that next actually. So in magnesium, as I told you, you have three shells, and even in sulfur you have three shells. But then the thing is that like in sulfur you have it's in group 6, right? So you have like 6 electrons, and then in S2 minus you actually gain 2 electrons, right? So to form S2 minus. So then that means that in S2 minus you also have three shells. Whereas for Mg2 plus, what happens is that this is Mg, right? This is magnesium. But when Mg2 plus is formed, basically magnesium loses its two valence electrons. So now it just has two shells, right? So Mg2 plus has only two shells, whereas Mg has three shells, right? So obviously that's not a very good drawing, but it's hard to draw concentric circles. But anyways, the point is that obviously because Mg has like three occupied shells, whereas Mg2 plus only has two. So that's why obviously the in for the like in the case of magnesium, the magnesium atom has a greater radius than the magnesium ion. So basically, Mg is like radius of Mg is greater than radius of Mg2 plus, right? So Mg is greater than Mg2 plus. So basically A or B should be right here. Because these two are wrong, and Mg has a greater radius than Mg2 plus. Okay. Now if you look at sulfur, the thing about sulfur is that two electrons got added, right? So because of that, the nuclear charge, it remains the same, obviously, because it has still the same number of protons. But because two electrons got added to the sulfur atom to become, the sulfide ion S2 minus. So because of that, now the nuclear charge is divided amongst more electrons, right? Like initially, sulfur had like 16 electrons, but now it has 18 electrons. So instead of the nuclear charge being divided between 16 electrons, it's divided between 18 electrons. And because of that, the nuclear force of attraction on each valence electron is less, right? Like now it has a complete opposite, and the nuclear force of attraction on each valence electron is less. And because of that, the S2 minus ion is like slightly bigger than the sulfur atom, like the radius of it. So basically, S2 minus radius is greater than sulfur radius, because the nuclear, like in sulfur, there is greater nuclear force of attraction on each individual valence electron, and so the nuclear, like the valence shell is pulled in a bit more in sulfur, whereas in S2 minus, because there are two more electrons added, so the nuclear force of attraction is divided amongst more electrons, so it's the valence shell is a bit uh, more like less attracted to the nucleus, so it's a bit more, it's a S2 minus is a bit bigger than S sulfur. So yeah, that's the logic, and so I have two ticks on B, so B is going to be my answer. Hopefully that makes sense. Again, if I make any mistakes or anything, you guys can tell me in the comments, okay? Now, question number 13. Which graph correctly shows relative electronegativity plotted against relative atomic radius for the elements sodium, magnesium, aluminum, and silicon? Okay. So, okay, let's look at electronegativity first. So again, electronegativity has a similar trend to the, how do you call it, the ionization energy and stuff, right? So I write down, I'll just show it on the periodic table. So from sodium to magnesium to aluminum to silicon, phosphorus, sulfur, argon, the number of shells is remaining the same, right? So shielding effect is fairly similar, and even the atomic radius, like from what we learned in the last question, it just decreases slightly. But the main thing is that the proton number is increasing, right, from 11 to 12, 13, 14, 15, 16, 17. And because the proton number is increasing, the nuclear charge increases on and the nuclear charge increases, and so because of that, the nuclear force of attraction on the valence electrons um, also increases, and so then the atomic radius decreases and all. But that same logic basically implies the electronegativity also increases across the period, like uh, yeah. So just like how across a period ionization energy increases because of greater nuclear force of attraction on the valence electrons. So yeah, then electronegativity will increase across the period, and again, electronegativity decreases across the groups. So basically, that means that if you're comparing sodium, magnesium, aluminum, silicon, silicon should have the greatest electronegativity. So silicon should be the peak here. So that's not the case in C. That's not the case in A. In B, we have silicon highest, then we have aluminum, magnesium, sodium lower than that. Sodium is the lowest. So B or D could be valid options. Now we have to compare the atomic radii. And from the previous question, actually, we even saw, like I told you already, that the atomic radius decreases slightly across a period because of the, like, the same number of shells. So shielding effect is fairly similar, but then the dominant change is that the nuclear charge is increasing, and so because of that, the nuclear force of attraction on the valence electrons increases, and because of that, the atomic, like the valence shell gets pulled in a bit, and so the atomic radius decreases slightly across a period, and because of that, basically silicon will have the least atomic radius out of these four, so it should be here, which is the case in B, but not the case in D. So D is out, and A is the correct answer, where sodium has the greatest, and magnesium has less, smaller, like a smaller radius, than aluminum atom has a smaller radius than that, and silicon atom has the smallest radius out of the four. So B should be the correct answer, and so I'm going to circle B. Okay. So yeah, next question. Trends are seen in the physical and chemical properties of the elements of group 2 and their compounds, which property shows a decrease from magnesium to barium. So if I just write down the elements of group 2, so, okay, that's it. P. Mukiraka Sarvara, that's how I remember it. My cousin taught me. Okay, and then now, which property shows a decrease, right? So the rate of the reaction between the element and dilute hydrochloric acid that should decrease. So that's an increase actually. The rate of the reaction between group 2 element and then dilute hydrochloric acid increases down the group. Why is that? Because imagine we have magnesium, which is just like this. Then barium, for example, will have a bigger, atomic radius, and because of that, if this is the nucleus, imagine this is the nucleus. Okay, so the valence electrons in magnesium, like the two valence electrons, are much closer to the nucleus, whereas in barium, they're much further away from the nucleus. So in barium, the two valence electrons are much more easily lost, and so barium atom is more reactive compared to the magnesium atom, which has like strong. The valence electrons have stronger nuclear pull from the nucleus, right? So there's there's stronger nuclear force of attraction in magnesium atom compared to barium atom. So barium atom loses its electrons more readily, and because of that, it is more reactive. So that's the trend down the group, that the rate of reaction between the element and dilute hydrochloric acid increases, right? And then as for the solubility of the hydroxides increases down group 2. That's more of like the logic behind that is more of an A2 thing. But yeah, the solubility of the hydroxides increases down group 2. So again, we need to show a decrease in trend, which is not the case in A or B. So A or B are out. As for the solubility of the sulfates, again, it's an A2 thing. The solubility of the sulfates decreases down group 2, right? So it's basically if you have like MgSO4 versus BaSO4. So NgSO4 will be less will be more soluble, and then BaSO4 will be less soluble. So BaSO4 will basically form a precipitate, whereas MgSO4 is soluble, right? So the solubility of the sulfates, group 2 sulfates, decreases down the group from magnesium to barium. And then the temperature of decomposition of the carbonates, again, that's an interesting. So but then yeah, basically down the group, like if you have magnesium, like Mg2 plus, imagine you have Mg2 plus, and then on the other hand you have Ba2 plus. So Mg2 plus is like both of them have a 2 plus charge, but then Mg2 plus is a smaller ion. So because of that, it polarizes the CO3 to, because Mg2 plus is a smaller ion, so it has a greater charge density, right? Charge density is basically charge of the ion over the size of the ion. So because Mg2 plus has a smaller size, so it will have a greater charge density, right? And because of that, it's going to polarize or distort the CO3 2 minus ion more as compared to Ba2 plus. So that means that Mg Mg uh, Mg's CO3 will decompose more readily than what do you call it, than BaCO3. So MgCO3 has a lower decomposition temperature. So decomposition temperature of the carbonates increases down the group basically. So A, B, and D are wrong, and so C is the correct answer. Solubility of the sulfates decreases down the group, whereas all other three trends um, increase down group 2. Okay, so now question number 15. Calcium oxide is added to water and the resulting mixture is filtered. This filtrate is X. When carbon dioxide is bubbled through filtrate X, a white precipitate is formed. Okay, now which equation for this reaction of filtrate X with carbon dioxide is correct? Okay, so let me see. So basically, initially we have the reaction between CaO and H2O, right? So metal oxide plus water gives you a metal hydroxide. So CaO plus H2O should give you CaOH twice, right? And then this is X, so this filtrate is X, COH twice, and then COH twice is basically reacted with carbon dioxide, isn't it? So COH twice plus CO2 gives you CaCO3 plus H2O. That should be the most likely products. Those should be the most likely products. And then which equation for this reaction of filtrate X with carbon dioxide is correct? So they want the second equation. So let me see if any of the options match with the equation I got. That's not the first one. COH twice plus CO2 gives CaO plus H2CO3. H2CO3 is it? No, they said a white precipitate is formed. No, that's not very likely in my opinion. I don't know, man. I don't think so. And then this one, CO plus H2 plus CO2 again. That's not what I got. This is what I got. COH twice plus CO2 gives you CO3 plus H2. So I'm going to take D as the answer because that matches with what I got, honestly. So yeah, D is the answer. Okay, now next question. Question number 16. Element X reacts with cold dilute aqueous sodium hydroxide to form two different chlorine containing products, Y and Z. Okay, now what are the states of chlorine in Y and Z? Okay, so basically element X is basically chlorine, right? So obviously, so Cl2 is how else would you get chlorine containing products? Basically Cl2 plus NaOH gives you NaClO plus NaCl plus H2 2 NaOH. And is that balanced? Is that balanced? It seems to be balanced. Okay. So now I have this equation. This is the equation for the reaction of chlorine with cold dilute aqueous sodium hydroxide, right? Now, what are the oxidations? This is X and this is Y and this is Z, or you could take that as Y, like you could switch the order. But what are the oxidation states of chlorine in Y and Z? So let me take this as Y. So NaClO. So there you have the Na plus ion and the ClO minus ion. Right? So in ClO minus, let's take the oxidation state of chlorine is X. Oxygen has a fixed oxidation state of -2, so X -2, and the overall charge of the ClO minus ion is just -1. We're going to equate this to -1, then X equals -1 plus 2, so X equals to +1. So in NaClO, your chlorine has an oxidation state of +1, okay, 1 plus. Now in NaCl on the other hand, in NaCl you have Na plus and Cl minus, right? So obviously Cl minus will have an oxidation state of -1, right? So we have +1 and -1. So is that any option? Now A, B will obviously be wrong. D is also wrong, and C matches with what we got, like -1 +1 or +1 -1. Depends which one you take as Y, which one you take as Z. Like you could take this as Z as well. This one is Y. Doesn't matter. But the point is one is +1 and the other one is -1, right? So +1 -1. So yeah, C is going to be the answer then. Then next question. A powder is known to be either a single sodium halide or a mixture of two sodium halides. Okay, now a sample of the powder was dissolved in water. And then aqueous silver nitrate was added, and the pale yellow precipitate was formed. Okay, pale yellow precipitate. So when concentrated aqueous ammonia was then added, this precipitate partly dissolved, leaving a darker yellow precipitate. Okay, so they're saying it's either a single sodium halide or a mixture of two sodium halides. I believe it's two sodium halides because, like, initially it had a pale yellow precipitate and then partly dissolved, leaving a darker yellow precipitate. So that implies that there must be more than one sodium, like, there must be more than one uh, precipitate at work there. And so I'm going to eliminate A and B on that basis and use, the colors of the precipitates would get like AgCl, AgBr, or AgI. So this AgCl would be white per se, and AgBr would be creamish, and then AgI is yellow, right? And so I would say that because they said that this precipitate partly dissolved, leaving a darker yellow precipitate. So in the end, when the precipitate had dissolved, and know that concentrated aqueous ammonia can dissolve both of these, right? Like AgCl can also dissolve in concentrated aqueous ammonia, and AgBr can also dissolve in concentrated aqueous ammonia. Whereas dilute aqueous ammonia would only dissolve AgCl, right? But since it's concentrated aqueous ammonia, it could dissolve AgCl or AgBr. So I'm not sure if the first one is AgCl or AgBr. But then the second precipitate, like out of the two precipitates, would definitely be, because it's a darker yellow precipitate after you add concentrated aqueous ammonia. So that would definitely be AgI because AgI is a yellow precipitate, right? So definitely there would be AgI. Second one I'm not sure about. So if you look at C and D now, so the only one which has sodium iodide mentioned, you know, so basically sodium iodide when it reacts with silver nitrate, you get AgI. And so D is the only one which has sodium iodide mentioned. And so I'm going to eliminate C as well because that's sodium chloride and sodium bromide. Sodium chloride is white. Sorry, not sodium chloride, but silver chloride would be white. The precipitate form when it reacts with silver nitrate. And then sodium bromide AGPR would be a cream color. So that doesn't make sense. Like, how would you get yellow from that? But D, you could definitely get yellow from that because sodium iodide would be yellow. There's a mixture of sodium chloride, like, sorry, not sodium iodide again. Why am I getting this wrong? But I mean silver iodide would be yellow, and silver chloride, silver iodide would be a lighter yellow. So pale yellow precipitate was formed, and then when you added concentrated ammonia, that pale yellow precipitate partly dissolved because the silver chloride dissolved in the concentrated ammonia, right? And so you only had silver iodide left, which doesn't dissolve in concentrated aqueous ammonia. Obviously, not in dilute aqueous ammonia either. So it's just, yeah, it doesn't dissolve in either of them. So you still have the silver iodide left, and that's why, yeah, you got the dark yellow precipitate after that. So yeah, basically D will be the answer. So it's a mixture of sodium chloride and sodium iodide. Okay. Now, next question. Question number 18. The ammonium ion is formed by the following reaction. So NH3 plus H plus gives you NH4 plus. Now, which statement about the species involved in this reaction is correct? The ammonia molecule contains a dative covalent bond. Well, that's obviously wrong. If I draw out the ammonia molecule, right? So it's like there's this lone pair here, there's H, H, H. So basically there's three covalent bonds and one lone pair in NH3. There's no dative covalent bond, right? That's wrong. Now the ammonium ion is a Bronsted-Lowry base as it has accepted a proton. That's wrong. We can see clearly here that NH3, that's the ammonia molecule, has accepted H plus. So if anything, NH3 is the base and NH4 plus is its conjugate acid, right? So NH3 plus, NH4 plus is a conjugate acid. So should have said it's an acid or a Bronsted-Lowry acid. Should have said that. They said it's a base, which is wrong because the ammonia molecule is the Bronsted-Lowry base, not the ammonium ion. So that's wrong. A and B are both wrong. Now, option C, the H and H bond angle changes from 107 degrees in ammonia to 90 degrees in the ammonium ion. And that's also quite obviously wrong. Like in ammonia, you have three sigma bonds and one lone pair. So 3 plus 1 equals 4. So the steric number, which is the total number of sigma bonds plus lone pairs in the atom friend in the bond angle, so that's 4. Is 4. The steric number is 4, and because of that, the bond angle should be at 109.5 degrees in ammonia, but because of the lone pair, it gets reduced by 2.5 degrees approximately, and so it becomes 107 degrees. Okay, so the bond angle in ammonia, yes, it's 107.0 degrees. Okay, so that part is right. But then if you look at ammonium ion, where you have, and now in ammonium ion you have a dative bond, right? Because this lone pair that ammonia had, no, that's not very, you can draw it, not that very, not very clearly, but this gets deleted to the H plus basically, and then you still have those other bonds to the hydrogens, right? These ones. And yeah, and then there's obviously an overall plus charge because of that H plus. So in this ion now you have four sigma bonds, one, two, three, four, right? So four sigma bonds and no lone pairs. So that means again the steric number is 4, so 109.5 degrees. But this time because there's no lone pair in NH4 plus, so it just remains 109.5 degrees. So in NH3 the geometry was actually pyramidal, but in NH4 plus your geometry is tetrahedral, right? So the bond angle is 109.5 degrees, and so it's going from 107 degrees in ammonia to 109.5 degrees in the ammonium ion, right? So basically that means C is also wrong. Okay, and because A, B, and C are all wrong, so D must be the correct answer. But let's read the option. The number of electrons surrounding each nitrogen atom does not change. Okay, so if you look at ammonia NH3, you have two electrons here, and then in this NH bond, there's two more electrons, so 2 plus 2 equals 4. Then in this one, there's also two electrons, so 6, and then this one, there's also two electrons, so 2 plus 4 plus, yeah, so it's 8 in total. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons around this nitrogen atom here. And then in the ammonium ion, again, you have two electrons being donated to the H plus. So there's a dative covalent bond there. So 1, 2, and then here as well, 3, 4. Now that's not being highlighted very well, but 3, 4. Then okay, this is going, yeah, the highlighter is sometimes annoying, but that's 5, 6. And then again, there's 7 and yeah, 8. Okay, so again, this one is also surrounded by 8 electrons. And so yeah, 8 electrons surrounding this nitrogen atom, 8 electrons surrounding that nitrogen atom. So the number of electrons surrounding each nitrogen atom does not change. That is true. Okay, now next question, question number 19. A chemist took two cubic decimeters of nitrogen gas measured under room conditions and reacted with a large volume of the hydrogen gas to produce ammonia. Only 15% of the nitrogen gas reacted to produce ammonia. Which mass of ammonia was formed? Okay, so let's write down the equation first. So N2 plus 3H2 gives you 2NH2. Actually, I should put that double-headed uh, like that. So equilibrium thing, and then okay, so we have 2.00 cubic decimeters of nitrogen gas, right? So how many moles of nitrogen gas do I have? So it's under room conditions, right? So let me say it's N equals V over 24. We can use that formula, V over 24.0, because you know, look, the data book would states it. I mean, now we don't get the data book, but it still state that page of important values in the periodic table, right? So if you look at this over here, it says that at room conditions is the molar volume of gas is 24.0 cubic decimeters per mole. So yeah, n equals 0 24.0, and so you'll just do 2.00 over 24.0. So that is 2 over 24 is 0.0833, right? So 0.08333, and this 3 means recurring, 3 recurring, okay? So 0.083 moles of N2, and then only 15% of the nitrogen gas reacted to produce ammonia. So basically 15% of this 0.0833333333, right? So just do that in the calculator. So the answer you got times 15 over 100. So you get basically you get 0.0125 moles of nitrogen gas reacting out. Like 15% of 0.083333 is 0.0125. Okay, so 0.0125 moles of N2 means that since there's a 1:2 ratio between N2 and 2 NH3, so just do 0.0125 times 2 to get the moles of NH3 formed, which is going to be 0.025 moles. Okay, so 0.025 moles of NH3, or the MR, or the molar mass of NH3, is basically 14.0 plus 1.00 times 3, so that's basically 17.0 grams per mole, right? So yeah, now what's the mass going to be? Mass is equals to N times MR, right? So moles are 0.025 as I calculated, and then MR will be 17.0. So now calculate this out, and you get 0.425 grams of ammonia formed. That's option B. So B will be our answer. Okay, now next question, question number 20. A carbonyl compound X will react with HCN in the presence of NaCN to make a compound of Mr85. Compound X does not react with Fehling reagent. So they said that X does not react with Fehling's reagent, right? And because of that, like Fehling's reagent is a test for aldehydes, right? So that means that X is not an aldehyde, but it's still a carbonyl compound, right? We can mention that in the question. So it must be a ketone. Then if it's not an aldehyde, it must be a ketone. So if it's because it's not an aldehyde, it does not react with Fehling's reagent, right? So it's not an aldehyde. So we can already eliminate option A, which is butanal, and we can eliminate option C as well, which is propanol, because those both are aldehydes. But option B is butanone, option D is propanone. So we cannot eliminate those yet because those are ketones. Okay. So now let's look at the next part, which is said MR is 85. So if I draw out butanone, butanone looks like this kind of, okay, and whereas propanone looks like this, right? So now if I'm reacting them with HCN in the presence of NaCN, it's basically that nucleophilic addition reaction, and I will get the product of that will be something like this, right? OH and C. Okay, that doesn't look very pretty. Uh, CN here, okay, and then whereas this one will give me OH CN, right? So that is what I get basically. And now we will find, like, they said the MR is 85. So let me find out what the MR of this compound is. So let me calculate it out. Okay, so just make use another color. It's this one, and make an arrow here, and then MR equals to. So firstly, how many carbon atoms do you have? I have 1, 2, 3, 4, 5 carbon atoms. Okay, so 12.0 times 5, because the relative atomic mass of carbon is 12. So 12 times 5. And how many hydrogen atoms do I have? So I have 1, 2, 3 hydrogen atoms here, then 4, 5, 6, 7, 8, 9. Okay, so I have 9 hydrogen atoms. So 1.00 times 9. And then what other atoms do I have? I just have this oxygen atom, which is 16.0. It's relative to mass, and then nitrogen. I have as well nitrogen as well. So that's 14.0, right? So now what is the MR I get? So 12 times 5 plus 9, 16 plus 14. So that gives me 99. If I'm not wrong, I could be wrong. No, 99 here, and 0, let me make it. And then we shall do the same thing for this one. Like that means that it's not the right answer, right? So I guess B will be wrong, and I would assume that D is the correct answer then, because butanone, this product that I got from butanone, after the addition reaction, nucleophilic addition reaction, does not have an what do you call it, an MR of 85. It has an MR of 99.0 grams per mole. So now I will try out with this one, which I got from propanol. So that's how many carbon atoms does it have? It has one, two, three, four carbon atoms. So that will be 12.0 times 4. Plus now it has one nitrogen atom, one oxygen atom, so 14.0 plus 16.0. And then how many hydrogens does it have? One, two, three, then, 4, 5, 6, and then 7, right? So it has 7 what do you call them, hydrogen atoms, right? So now if we calculate out the molar mass, so that will be 48 plus 18, 16, 7. That is actually 85.3. That's a good thing. I was like, oh no, what if all the options are wrong and I have to do the question again? So yeah, yeah, okay, 85.0 grams per mole. That's what we got. So that means again it's confirmed that D must be the correct answer. So yeah, D is the answer. And then we go to the next question. So geraniol and linalool, I don't know how to pronounce that, are compounds found in some flower fragrances. That's a cool fact. Okay, now geraniol and linalool. Which statement is correct? They are chain isomers of each other. Hmm. So if they're chain isomers, then they must differ in like the number of atoms in their chain. I suppose their parent chain. So one in geraniol, it's 1, 2, 3, 4, 5, 6, 7, 8. So it's like the chain is 8 carbon atoms long, and 1, 2, 3, 4, 5, 6, 7, 8. Again, it linalool as well as 8 carbon atoms. So they're not chain isomers then, are they? If they're geometrical isomers, then they must have the same structure or formulae, but they just differ in their special arrangements, right? Around the CC double bond. But this whole part is identical in both of them. So it can't be anything to do with this CH, I think. I mean, honestly, they wouldn't have. Yeah, because this part is the same completely. This carbon CC double bond cannot even have cis trans, because this carbon atom in the CC double bond has like two CH3 groups attached to it, and the CH3 groups are identical, right? So this one cannot have cis trans. But if I look at the other CC double bond, which is like this one, it could have cis trans, because in this carbon atom here has two different groups attached to it, H and CH2OH, and this other carbon atom also has two different groups attached to this whole thing and CH2. But if you look at linalool, or however it's pronounced, then it's different, because this CC double bond here, like it cannot have cis trans, can it? Because um, it has two, like this carbon atom, which I will highlight right now, it has two H atoms attached to it, which means it has two of the same groups attached to it, which means it cannot show cis trans. So actually, they're not cis trans isomers of geometrical isomers of each other, because if they had been, we see the only difference would be that geraniol will look like this, but then linalool would just look like this. Like you have CH2OH here and H here. So that's the difference. But that's not the difference between geraniol and linalool. So they cannot be geometrical isomers, definitely. Definitely isomers, but not geometrical isomers. Now, optical isomers, they cannot be optical isomers either, because if they were optical isomers, like they will not be drawn in this form. Their difference would be highlighted using those diagrams which have dots and the wedges, dots and wedges, and the three-dimensional diagram basically to show that they're mirror images and whatever. But that's not what's drawn here, so that just shows that they're not optical isomers. But really, I don't see any chiral carbon atoms in general, at least. But if I look at linear dual, I do see one carbon atom which is here. But again, they're not drawn three-dimensional diagrams. So yeah, they're not optical isomers either. So then that only leaves option D. They're positional isomers of each other. And basically, in a positional isomer, what would be the difference? The difference would be that the position of the functional group would be different, right? So what I would say is that again, the parts that I've circled, they're the same in both geranyol and linear. But if you look at geraniol, then if I take this as my, the first carbon in my chain, so 1, 2, 3, so my CC double bond is between my second and third carbon atom, whereas in linear dual, my CC double bond is between my first and second carbon atom, right? So my the carbon-carbon double bond for alkene is between the first and second carbon atom. This is, it's hard to highlight stuff. But anyways, it's between the first and second carbon atom, whereas in geraniol is between the second and third carbon atom. So yeah, the position of the functional group is different in both of them. So I would say that the most likely option is that they are positional isomers of each other. So yeah, the answer is D. Okay, next question number 22. Which equation represents the initiation step of the substitution reaction between methane and chlorine? So in the initiation step, you have free radicals formed, right, from a molecule. So basically this one, B and D, they're both forming ions, not free radicals. So B and D can immediately eliminate. But then if you look at A and C, the thing is that the answer would be C, definitely not A. And why is that? It's because in A you have this H free radical being formed, whereas usually in free radical substitution you tend not to get this hydrogen free radical as an isolated product. I mean, it's not very likely. So A is wrong for that reason, and also like if you've studied this case study, like Cl2 this reaction with methane, so then you do see that the first step is actually this, right? Like Cl2 gives you 2Cl. So you could think of it as a recall question or a logic question, kind of. But yeah, for that reason, C is the correct answer. Like you're getting from Cl2 molecule, you're getting two free radicals, which are chlorine free radicals. Okay, and yeah, so the answer is C. Next question. Aqueous sodium hydroxide reacts with one bromopropane, that's a hydrolysis reaction, to give propane 1 mole. So if I draw out one bromopropane, it's something like this, right? No, my drawing skills are not that good, but yes, this is one bromopropane and this is propane 1 mole. Now, which should be included in a diagram of the first step in the mechanism? Okay, maybe I should draw the mechanism out instead of this. So we have again one bromopropane. And one bromopropane is a primary halogenoalkane, right? So since it's a primary halogenoalkane, it undergoes SN2 mechanism for the nucleophilic substitution, and because of that, there's no stable carbocation. Intermediate is just like there's a transition state formed, so it's basically a one-step mechanism. And so when you have from NaOH, you get the OH minus nucleophile, right? And what happens is that this carbon here is partially positive, this one, and this bromine is partially negative. So this bond breaks, and this lone pair of the OH attacks the carbon atom, and then you basically get, well, you get the transition state, but after the transition state, you get this OH, and you get Br minus as well. So yeah, and then I didn't draw the transition state, but you could draw the transition state if you like. And now, what are they asking? Like which one? It's not. It's like if I'm looking at option D, it's definitely not homolytic fission of the CBr bond. This is heterolytic fission. Like Br minus gets both both the electrons, and it's like it's not heterolytic fission where one electron goes to the carbon, one electron goes to the bromine. No, it's because they're both partially charged, so it's heterolytic fission. And then if I look at option C, a curly arrow from the CBr bond to the C atom. It's not from the CBr bond to the C atom, it's from the CBr bond to the Br atom. So this is wrong. C is also wrong factually. And then option D is a curly arrow from the partially positive carbon atom of one bromopropane to the OH minus ion. No, it's not from the partially positive carbon atom to the OH minus ion, from the lone pair on the OH minus ion to the partially positive carbon atom. So that's wrong as well. And then A should be the correct answer. Then I suppose if I've not done it wrong, well, let me just read A. And it says a curly arrow from a lone pair on the OH minus ion to the partially positive carbon atom of one bromopropane, which is what I said exactly right now. So yeah, A is the correct answer. And yeah, so yeah. Then next question. A sample of 2.76 grams of ethanol, which is CH3, CH2, OH, was mixed with an excess of acidified potassium dichromate, so that's oxidation. And then the reaction mixture was boiled in reflux for 1 hour, so definitely you would, because it's oxidation and it's boiled in reflux for 1 hour, so we definitely get CH3COOH from that. And the required organic product was then collected by distillation. Okay, nice. And this is 2.76 grams of ethanol. Okay, and its oxidation, the ratio between CH3, CH2OH and CH3COOH is 1:1. Okay, so yes, now this is 2.76 grams. If I find out what is the molar mass of CH3, CH2OH, so I have two carbon atoms, that's 12 times 2, plus we have 3, 4, 5, 6, 6 hydrogen atoms, so that's 1 times 6, and we also have one oxygen atom, so that's plus 16. So you get the, what do you call it, the molecular mass or the molar mass as 46.0 grams per mole. Okay, now we have to find the moles of CH3, CH2OH, so N equals M over MR, right? So 2.76 divided by 46.0. So 2.76 divided by 46.0 will give you 0.0600 moles of CH3, CH2OH. Now again, as I told you, it's 1:1 molar ratio, so CH3COOH, like the ethanoic acid, will also be the yield, the for like there theoretically you would get 0.0600 moles of it. Okay, but then the mass you would get from that would be n times mr. So now if I find out the molar mass of CH3COOH, then again you have two carbon atoms with 12 times 2, which is 24, and then you have four hydrogen atoms, that's 4 times 1. So then you have and then you have two oxygen atoms, so that's 16 times 2, 32. And so if you add all of that, you get 60.0 grams per mole as the molar mass. Now the moles will be, sorry, we already have the moles, we're trying to find the mass. So this is a theoretical mass, right? You know, had the reaction gone to completion, which obviously didn't happen. So M equals N times MR, so the moles times the molar mass, so that will be 0.0600 times 60.0, so that will be 3.6 grams, theoretically. Okay. Now, which means that three significant figures, 3.60 grams. Now, the yield of product was 75.0, so it's not actually 3.60. That's the theoretical one, but actually got 75%, right? So that 75.0 over 100 equals to the actual yield, which is x over the theoretical yield, which is 3.60. So now x is equals to 75% of 3.60, which is going to be 2.70 grams. So actually, like the actual yield or the theoretical yield equals to 75%, and that gives you the actual yield, like the mass of product collected, as 2.70 grams, which is option D. Okay, so I'm going to circle that. Now, next question. I'll just write this over here actually. Make space for the next question. Compound X is a single pure optical isomer, and I think that's a full stop. Yeah, that makes more sense. I was confused for a second. Okay, X is heated with an excess of concentrated H2SO4. So that means that basically, you know, you see OH here. So that means if you're heating it concentrated H2SO4 and excess of that and blah, blah, blah. So that means it's basically dehydration of alcohol or like elimination of water, basically. Now, only one organic product is formed. Now, what could X be? So firstly, like you lose OH obviously when you're dehydrating the alcohol, and you lose H from the adjacent carbon atom. So imagine that I lose H from this carbon atom. So what product will I get? I will get, I'll draw it here. So 1, 2, 3, 4, 5, 6. I get this thing. Okay, I can write a bit bigger or maybe make the screen a bit bigger. Okay. So 1, 2, 3, 4, 5, 6. And then I am losing the hydrogen from this circled carbon atom, so there we have double bond formed here. So dehydration of an alcohol forms an alkene. Okay, remember that. That's why I get this product. Okay, or if alternatively I lose the OH obviously, but I lose the H from this carbon atom, so I could get this thing like this. Okay, now I have to just determine whether first one and the second one are different. So let me count the carbon atoms and stuff. Okay, so over here, make this as 1, 2, 3, 4, 5. Okay, so 5. Okay, now here Let me make this as, okay, wait, no, no, there's another way I could do this. So one there, and then two there, so there's a space of two here, but then one here, two here, three here. So obviously, these two compounds do seem to be different. Like the first one and second one that I got from dehydrating this alkene, these two are different isomers, right? So that means that because the question says that for X only one organic product is formed, that means A is wrong because I got two different ones, right? And now if you look at B, I could either lose, obviously I could lose OH and I could lose the H from this carbon atom, that's adjacent. And so I would get 1, 2, 3, 4, 5, 6, and this thing like this, and then I would get a double bond here. Or alternatively, I could have 1, 2, 3, 4, 5, 6, obviously, and I could lose this OH and the H from this carbon atom to the right. So then I would get a double bond here. Okay. Now I have to determine whether these two compounds are different from each other or the same. So let's see. Over here, 1, 2, so there's a difference of 2 here, and 1, 2, so the double bond is between these two here. So that's obviously different. So these two compounds are different. I'm not really even numbering them. I'm just saying the differences. Okay. So yeah, yes, these two compounds are different as well, which means that more than one isomer is formed, basically, right? As you can see. So that means that B is not the answer either. So it's now between C or D, and let us see which one it is out of these two. So let me see which isomer I can see. So C, I can lose this OH obviously, and this H from this carbon atom. So if I do that, I get 1, 2, 3, 4, 5, 6, and something like that. Okay, that doesn't. Like, I think I should make the screen bigger so that you can see it more clearly. But that's, I tried from a draw it. Okay, but as best as I could. But yeah, that's what you get. And is it a valid thing? 1, 2, 3, 4. Yeah, it seems like valid isomer. And then on the other hand, the other product I would get would be if I lose this OH, and then from the carbon adjacent to this carbon atom, I lose the H from this one. So then I would get this compound 1, 2, 3, 4, 5, 6, and um, I basically have a double bond between these two. Right now, is that valid? 1, 2, 3, 4, 1, 2. Yeah, that seems like a valid compound as well. Now, if I count the carbon atoms, obviously this one and this one are two different compounds. So yeah, you get more than one isomer, which means that option C seems to be wrong as well. So option D must be the correct answer, but obviously let me just check. Okay, so I will check, and then here what will happen is that I will lose the OH from this carbon atom, and then from the adjacent carbon atom, which is this carbon atom, I will lose H. Okay, that's obviously just one product, isn't it? So yeah, this one definitely does form only one product, which is like this. CH2. Yeah. Is this valid? 1, 2, 3, 4. Yeah, it's got flatness forming four single bonds. Single bonds. Not single bonds, actually, I shouldn't say that. Four bonds. Well, there's one pi bonds for this. Double bonds. One single bond and one pi bond. But basically, there's only one isomer that can be formed from D. I can't think of any other isomer at least. So that means that probably D is the correct answer because only one organic product is formed, right? So I will say that D is the correct answer. Okay, so yeah. Now, next question. 2-bromo-2-methyl propane undergoes nucleophilic substitution when heated and reflux with an aqueous solution of sodium hydroxide. Which row is correct? Okay, so let me draw out 2-bromo-2-methyl propane. So it's like this. Then you have on the second carbon atom, you have a bromine, and you have a methyl group as well. Okay, so now it undergoes nucleophilic substitution. Now this is a this carbon atom that the bromine is attached to, this one that I'm highlighting, it's attached to three other carbon atoms directly, right? Like this one, and this one. So that means tertiary halogen or alkane, tertiary bromo alkane, and because of that, it undergoes SN1 mechanism, SN1 nucleophile substitution mechanism. So that's why it is a slow mechanism, like it has two steps, and there will be an intermediate formed, a highly stable carbocation intermediate, because it has three electron releasing alkyl groups, right? So now the mechanism, as I told you, is SN1. So that means either A or B. Now the intermediate carbocation is stabilized by the inductive effect of the methyl groups. That's the correct answer. Not destabilized. See, destabilized is wrong. So D cannot be the right answer, obviously. And the other thing is that the hydroxide ion is helped in its approach to the what? Let me read this. The hydroxide ion is helped in its approach to the central atom by the methyl groups. The hydroxide ion is hindered in its approach to the central carbon atom by the methyl groups. Okay, so what, what? Central carbon atom by the methyl groups. Hmm. Let me think about this. I mean, there's that thing called steric hindrance, right? So I don't really know much about it, but like because of that steric hindrance, like definitely the hydroxide ion is not helped in its approach. If anything, it would be hindered in its approach, right? Let's say A is wrong, but that part in C would be right. But again, it would not be right for SN2. It would be right for SN1, where there are like three methyl groups, right? So that's where there is the steric hindrance, I would think. Again, guys, if I'm doing anything wrong, just tell me in the comments, right? But yeah, I would say that the hydroxide ion is hindered in its approach to the central carbon atoms by the methyl groups for SN1. Then the statement in A is wrong, or it's helped in its approach. That's wrong. So again, the one where I have two ticks is B, so I would say B is the answer. The intermediate carbocation is stabilized by the inductive effect of methyl groups. That's definitely true, right? So yeah. Anyways, the answer is B. So now I'll go to the next question. H2N and HC6H3NO2 twice structural formula of 2,4-D and pH. Many but not all organic reactions need to be heated before reaction occurs. Yeah. Now, which reaction occurs at a good rate at room temperature, which is 20 degrees Celsius? So C10H2 gives you C8H18 plus C2H4. That's cracking, right? So cracking does require a high temperature, right? Like for example, like a very high temperature, maybe like 450 degrees Celsius, I would say, above that, very high temperature. Yeah. So catalytic cracking requires, or catalytic cracking or thermal cracking. In fact, both of them. The difference is just that catalytic cracking requires a catalyst as well. Or the other one, thermal cracking, would be like high temperature, high pressure. Catalytic cracking is high temperature and catalyst. But anyways, the point is that they require a high temperature, both of them. So anyways, cracking requires a high temperature. The next one is C3, CH3, CH2, CH2Br plus NH3. And yeah, that requires, again, it requires a high temperature, like heated Russian of CO2 or whatever, right? So yeah, and then this one CH3 CH2 OH plus KBr, again that requires heat and reflux. So I would say that's strong as well. But then the next one, which is CH3 twice CO plus 240 and pH, then this gives this thing. So again, that is 240 and pH. The reaction of 240 and pH with carbonyl compounds does occur readily at room temperature, which is like, yeah, okay, 20 degrees Celsius. So yeah, that one is true. D is true. That's why such a good test, right? Like 240 pH is a good test for carbonyls because it occurs at room temperature. And my screen is okay now. It's fine. It was black for a second. Okay, now question number 28. A carboxylic acid P has no possible chain isomers. It reacts with an alcohol Q that has only one positional isomer. What could be the ester form from a reaction between P and Q? Okay, so in the first option we have butyl propanoate. So butyl propanoate. So that means this is the alcohol. Pen like this. Okay, butyl. That means this is the alcohol part, and the propanoate means that's the carboxylic acid part. Right. So butyl means I had butanol and propanoic acid. Right. So propanoic acid, yeah, it does not have any chain isomers. That is true. And what about butanol? Butanol would have one position isomer. Yes, it would have like butanol. This is butanol, and that the chain the sorry the positional isomer possible is butane 2, right? So yeah, that does seem to be right because there's only one positional isomer of this alcohol Q, and P has no possible chain isomers, which is propanoic acid. So A seems to be right. So I would say A is the answer, but again, maybe we should check the other options as well, just to be sure. And so I will check option B as well, which is ethyl butanoate. So that means I have ethanol. Ethanol actually has no positional isomers, right? So that's immediately wrong because they said that it has only one positional isomer, which means it does have exactly one positional isomer. So if ethyl butanoate in ethanol you have no positional isomers, that means it's wrong, right? So that means it's wrong. So yeah, and then next we have pentyl ethanoate, which is basically you have pentyl, which means you have pentanol, and ethanoate means you have ethanoic acid, OH, COOH, and I don't know if I can draw that a bit better. But anyways, what's the point? Is that okay? So obviously P carboxylic acid, which has no possible chain isomers, that's right. And then what about pentanol? Pentanol, does it have any positional isomers? Yes, it does. It has pentane. That's pentane 1-ol that I drew before, and this is pentane 2-ol, and I have pentane 3-ol as well. So that means that it has more than one position isomer. So I need only one positional isomer. So that means C cannot be the right answer either because I need to have exactly one positional isomer for the alcohol, right? Now what about propyl pentanoate? So propyl pentanoate means I have propanol and I have pentanoic acid, right? So propanol, obviously it has only one positional isomer, which is right. But then there's propan 2. Then about pentanoate, if I look at pentanoate, does it have chain isomers? It has. Hmm, hmm. Let me think. Let me think. I mean, obviously, you could have, because this one is a 5 chain thing, right? So I could have, there's any others I could not, but like, I'm not pretty annoyed I could touch. Anyways, I eliminated B because of ethyl. Ethyl has no position. So ethanol, I mean. So anyways, about this one, propyl pentanoate. So this is one of them, and the other one I could have if I had like 4 carbon atoms in the parent chain, and then one branch, and then OH, right? Or maybe it could be like this, I suppose. But the point is that there can be branching, and there are chain isomers possible, basically. So because of that, one, two, three, four, five. And because of that, I will eliminate D because the carboxylic acid has to have no possible chain isomers for a question, like for that, this type of question to be right. Right, so that's why A is going to be the answer because A is the only one that's valid, right? So yeah. Then next we have question number 29. Let me just erase this stuff. I don't know why. I guess it's just fun to erase stuff. Anyways, which compound is chiral and reacts with Na2CO3 to give CO2? It's a chiral. So A does not seem to be chiral because for a chiral, for carbon atom to be chiral, you have to have it has to be bonded with single bonds to 4 different groups as well, right? So, in this one, this carbon atom is like C double bond OH, so it's bonded 2 times to the C because the double bond it cannot be, chiral carbon atom. Anyways, that's wrong, and even these two like they're double bonds and so also double bonds. So there's no chiral carbon atoms here, right? And then in this one, I think this one is chiral, right? So if I divide this molecule in half like this, then this side is not symmetrical to this side, right? And you have like basically 4 different groups attached then. This one and then this one and this one and this one. So there are 4 different groups attached. So that means that this carbon atom that this one that I'm putting a dot on, it is definitely a carbon atom. But then the problem is, does it react with Na2CO3? No, it doesn't because there's no CO2H group. OH cannot react with Na2CO3, can it? But whereas carboxylic acid group has, it has acidic like it's an acid, so it's an acidic group, so they obviously give the acid reactions. If I look at this option, which is option C, this carbon atom that I'm circling here, it does seem to be chiral as well, because it has one H group attached, then one this one uh, C HCOO group is attached as well. It's different from what I talked about earlier because it's like this, right? So this is single bond basically. The CO single bond is valid basically, and then yeah, it has four different groups attached basically, like H, CH2Br, and then O, COH, and then CH3. So yeah, this is chiral. And then because of the HCOO group, that means HCO like the COOH group. No, wait, no, it does not give a reaction with. Yeah, I'm wrong because this is HCO. That means it's an ester group, right? Not ester. It's not carboxylic acid, so it will not react with Na2CO3. Yeah, even the chiral, it will not react with ester. Na2CO3. So that's wrong, and then that means D must be the answer because it's the only option left really. But if I look at this carbon atom, it is chiral because it has one H group, one Br group, one COOH group, and one CH2CH3 group. So it has four different groups attached, and the CO2H group means that this compound will react with Na2CO3 to give you CO2 effervescence. So yeah, D is right, and that I will circle D. I already circled D in fact. And so now I'll go to the question number 13, which is which compound, when hydrolyzed, gives propanoic acid and propane 2O. So propanoic acid and propane 2O. So if I look at the first one, which is CH3CH2COO, so I'll just draw it out, and then CH2CH3. So 1, 2, 3, 3, and then on the second one it has CH3. So this is what they drew in the A, right? So now if I hydrolyze this, I get this compound plus OH, this, right? So does it give me propanoic acid? Yes, it does give me propanoic acid. And does it give me propane 2? Well, one, two, three, four. This one has four carbon atoms. It's definitely not propane 2, is it? So yeah, maybe that's a better way to do it actually. 1, 2, 3, 4. So I should have three carbon atoms on the left side, three of the CO, like of the OO, and three carbon atoms on the right side. So using that logic, I already eliminated A. Okay, so I didn't even need to do this working. You can easily eliminate A fast, I suppose. So yeah, and then if I look at B, it has CH3 twice, CHCOO, CH2, CH2. So the left side, you have one, two, three, four carbon atoms. So you don't get propanoic acid, you get a four carbon acid. And then on the right side, I have CH2, CH3, which again is two carbon atoms, not three. So I need three and three on both sides, like the carboxylic acid side and the alcohol side. So basically, this is wrong as well. B is wrong. And then C, one, two, three. So I have three here, which is right. And then on the right side, I have one, two, three. So three here as well, which seems to be right. So I would say C is right till now, but if D is also like that, then that means I have to look at the how what 1, 2, 3, 4. So on this side I have 4, it means it's wrong, and on the right side I have 1, 2, 3, which is right, but then on the left side I have 4 carbon atoms, which should be wrong because I need propanoic acid and I need propane 2O, right? So I need 3 carbon atoms on the left side and the right side. Whereas on the left side for D, I have CH2, 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 COO, means CH3, CH2, CH2, COO, which means butanoic acid, which is not what I want. So D is also not the correct answer, which means C is the correct answer. I have 3 carbon atoms in the carboxylic acid part and 3 carbon atoms in the what do you call it, the alcohol part. So therefore, C is my answer, and really, you don't even need to draw it out, you can just count. So yeah. Now next we are doing the section B thing. So let's do it. An isolated gaseous atom of element X has paired electrons in at least one of its 3D orbitals and has a filled 4s subshell. Okay, let me go down to my periodic table for this. I think we need to where you have to do the electronic configuration and stuff. So now, what could be the identity of element X? Okay. Oh my god, element X, it just sort of makes me feel like I'm reading something like Powerpuff Girls, or because element X, X. Anyways, it gives Powerpuff Girls vibes. Anyways, whatever. What was identity? So like iron. So let me see where iron is. Iron is here. So this is 1, 2, 3, 4. This is period 4. Period 4, and obviously this is the D block, right? So now what is the electronic configuration of iron end with? It ends with 1, 2, 3, 4, 5, 6. So 3d6. So 3d6. So let me just write it down. So iron has 26 electrons. Okay, so 26 E minus. So if I write down its electronic configuration, so it's S, so 1s2, 2s2, 2p6, 3s2, 3p6, with 4s2 because before that you have 4s2 and then you have 3d6, right? So 4s2, 3d6, and let me see if it's all adds up to 26 electrons. So 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6 is 26. Okay, so that's the iron, the electronic configuration of iron. Now, does it have paired electrons in at least one of its 3d orbitals? Yes, it does, because 3d6 means that it's like this. Wait, let me just draw it a bit more like this. 1, 2, 3, 4, 5, 6. So one of them is paired, definitely. And 4s2 is there as well. Filled 4s actually. So iron could be element X. Okay, and then if I look at gallium, where is gallium? I don't know where gallium is. Oh, I found it. Okay, it's next to zinc. So here's gallium. And this is the P block. Gallium is in the P block. So it ends in 4p1. And let me write down 31 electrons, right? So it should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then SSP, So P4p1. Now let me see if this adds up to how many? 31 electrons was it? Yeah. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 1. That's 31. Okay, good. So now, does it have a filled forest subshell? Yes, as you can see. And does it have at least one of its 3 electrons paired? Yes, it does. As you can see as well, 3 10 is fully filled, so all of them are paired in gallium. So gallium could also be element X. Now, if we look at copper, here's copper. So in copper, the 29 electrons, it will be 1s2, 2s2. It's in 3d1. 3d1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 3d9. Yeah, that's 9. So 3d9, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But then, it's just a thing that happens with copper. Like, you just make the 3d9 into 3d10. So the d subshell is stable and it's 3d10 or 3d5. So just make 3d9 into 3d10. So it becomes 3d10 and it becomes 4s1 3d10. So now 2 plus 2 plus 6 plus 2 plus 6 plus 1 plus 10, that is 29 electrons, which is copper. So yeah, this is the right configuration. And now, does it have a fully filled 4s subshell? No, it doesn't. It has 4s1, not 4s2. 310, yeah, it does have paired electrons in its 3d orbitals, but 4s1 means it does not have a fully filled 4s subshell. So that means that copper could not be element X because it does not have a filled 4s subshell, right? So that means that the answer is A and B. Sorry, 1 and 2, not 3. So 1 and 2 means that the answer has to be B. Okay? B. Yeah. Now, next question. Which allotropes of carbon have a giant molecular structure? Buckminster fullerene? No, it does not, because Buckminster fullerene is basically C60, right? So C60, the carbon atoms are limited in that. It's just 60. That's why it's a nanoparticle, and so it does not have a giant molecular structure. It has a finite number of carbon atoms, like a limited, like 60. 60, exact. So yeah, and diamond, on the other hand, and graphite are both giant molecular structures, giant macromolecules. So 2 and 3 are right, so therefore the answer is going to be C. Okay? Yeah. Now question number 33. The statements about endothermic reactions are right. So they're talking about reaction pathway diagrams in the first one, so I'll draw it. Something like that, I suppose. And because basically in endothermic reactions, your enthalpy change is positive, right? So it's like this. This is the reactants, and these are the products. We drew this in from an earlier question as well. So yeah, and this is the activation energy. Anyways, so the enthalpy change is positive. So on the reaction pathway diagram, the products of the reaction are lower than the reactants. So the products are actually higher. You can see the products are here, and then the reactants are down there. So basically, the products of the reaction are higher than the reactants. That means that statement 1 is wrong. If statement 1 is wrong, then actually 2 and 3 must be right. So then my answer is going to be C immediately. But you can read the options and figure it out. So let me read the options now. There is a net transfer of heat energy from the surroundings to the reacting system. From the surroundings to the reacting system, that is right. Like energy is absorbed, right, by the system. So yeah, that's right. That energy is absorbed into the system. So yeah, that's right. It's endothermic. So that is right. There's a net transfer of heat energy from the surroundings to the reacting system. And this third statement is that the total bond energies of the reactants is greater than the total bond energy of the products. If I See, how do we calculate delta H? Delta H is calculated by bonds broken, the enthalpy change of the bonds broken minus the enthalpy change of the bonds formed, because actually enthalpy, bond enthalpy is a positive value, right? So enthalpy change of bonds broken will be a positive value, and then bonds formed are also positive, but then because of the minus sign, like bonds formed will be a negative value, right? So if it's an endothermic reaction, we know that delta H is positive, right? Delta H is positive, which means that delta H is greater than 0. If delta H is greater than 0, that means it's again a positive value, which means that bonds broken, which takes B is greater than BF, right? So bonds broken is greater than bonds formed. Like the entropy change, the total bond enthalpy of the bonds broken is greater than the total bond enthalpy of the bonds formed. So the total bond energies of the reactants is greater than the total energies of the products. The bonds broken are of the reactants, and the bonds, so basically the reactants, which is basically the bonds broken, right? The reactants, the ones that have bonds broken, and the bonds are formed in the products, right? So the total bond energy of the reactants is greater than the total bond energy of the uh, like products. So what I said here, like bonds broken are greater than bonds formed, like the enthalpies. So because this is that is a positive value, right? So 3 is also a right statement for that reason. Hopefully, I did not make it a very weird explanation and you understood it. But again, if you have any questions, you can ask in the comments, or if I made a mistake, you can write in the comments as well. So yeah, 2 and 3 are correct. Okay. So now next question. The rate of chemical reactions can be increased by the addition of a suitable catalyst, for which reactions can a heterogeneous catalyst be used. So this, the first one is N2 plus 3H2 gives 2NH3. That's the Haber process, and Haber process you do use iron catalyst, right? So this is right. That's a heterogeneous catalyst because these are all gases, whereas iron is a solid. 2SO2 plus O2 gives 2SO3. That's again, it's right because again all of these are gases, whereas vanadium pentoxide, which is the V2O5, which is the catalyst used, is actually a solid. To my knowledge, at least, it's solid. So yeah, so it's also a heterogeneous fashion. And then 2NO plus 2CO gives you N2 plus 2CO2. So that's a reaction in the catalytic converter. And in the catalytic converter, these are all gases. And then you use, in the catalytic converter, you use platinum or palladium or rhodium. I'm not sure if rhodium is RH. I think that's the symbol of it. So again, those are solids, whereas these are all gases. The reactants are gases. So that means, again, it's a heterogeneous catalyst. So that's why for all these reactions, a heterogeneous catalyst can be used. So that means the answer is going to be A. Okay. Now, question number 35. Which chlorides, when added to water, can produce a solution with a pH of less than 5? So SiCl4, that would be correct because SiCl4, if I write down the reaction, SiCl4 plus 2H2O gives you SiO2 plus 4HCl. Wait a second, let me think about this. SiO2 is obviously a solid. And Cl, I mean, that's going to be a gas, but then I think I would say it's acidic, right? I mean, yeah, it's a liquid too. Yeah, should be right. So it would form an acidic thing, and then AlCl3 on the other hand, again, AlCl3 would also form an acidic solution. Really. Yeah, it should be acidic. I mean, more less than 5. I mean, because if I think about MgCl2 when it dissolves in water would actually give me a solution of pH around 6.5 from what I remember. So yeah, so it dissolves in water to give you a solution of around pH 6.5. It is close to neutral, but they're asking about a pH of less than 5, which is not the case. So I would say MgCl2 is wrong, but AlCl3 again gives you a highly acidic solution, and the the what do you call it? We write down it's actually a long list of reactions. Like first, the AlCl3 will sort of decompose into its like the ions, so Al3 plus and Cl minus, and then eventually the Al3 plus will become like AlH2O, should not be right, H2O 6 3 plus, which it's slowly sort of what should I say, like it decomposes or something, like decomposes, okay, yeah, that works, in water, so slowly it starts releasing protons, right? So it becomes 2 plus plus H plus, right? So one of the water molecules has decomposed, and this keeps on happening until these H pluses, these protons that are released, basically make the solution acidic. So that's why you get an acidic solution, as I mentioned. So it will have a very acidic solution, which will have a pH less than 5. Even for SiCO4, you'll have a acidic solution called an acidic solution. But MgCO2 is that one has pH 6.5, which is not less than 5. Obviously, 6.5 is greater than 5. So yeah, that's why I'm not counting 3, but 2 and 1 are right. And therefore, like 3 is definitely wrong, so 2 and 1 are right. And that's just going to be B. Okay, so yeah. Now, question number 36. Acid rain continues to be a problem. That is definitely true. Now, which statements about acid rain are correct? Acid rain is formed when oxides of nitrogen or oxides of sulfur react with water in the atmosphere. That's definitely true. Yeah, that part is true. When oxides of nitrogen or oxides of sulfur react with water in the atmosphere, then acid rain causes an increase in the concentration of heavy metal ions in water courses. That's also true because of the whole, like when acid rain occurs, then you get leaching, like the washing off of fertilizers from the soil into the nearby water bodies like the lakes, ponds, streams, whatever. So because of that washing off the fertilizers, then obviously the heavy metal ion concentration in those water bodies increases. Yeah, that's right. And the first one was also true because the acid rain is H2SO4 really, right? And also you can kind of think of it as H2SO4, but not really. It's more like H2SO4. But again, oxides of nitrogen are involved in that process, right? Like like I could write down the equations, I suppose. So it's like SO2 plus NO2 gives you SO3 plus NO. That's the first equation, and then later NO plus half O2 gives you NO2. So here you can see that NO2 and NO are acting as catalysts because you can sort of cancel them out on both sides of the equation, right? They're unchanged by the end of the reaction, but as basically they're saying that oxide of nitrogen or oxide of sulfur react with water in the atmosphere. So I mean, it's just true, like they're all involved in the process. I mean, acid rain is mainly H2SO4 really. So SO3 plus H2O gives you H2SO4 then. Um, you could really, if you want, you could have this reaction in the first one or the second one. So 1, 2, 3. But basically, you end up getting H2SO4, which is acid rain. So yeah, statement, I'm just proving how statement 1 is right, and then we show you how statement 2 is right. Now, got statement 3, which is that nitrogen dioxide will catalyze the formation of SO3 from SO2 in the atmosphere. I just showed you that right now, that nitrogen dioxide is this one, right? So nitrogen dioxide, it's acting as a catalyst because it's on the left side of the first equation and the right hand side of the second equation. And NO was on the right left side of the first equation, second equation, and the right side of the first equation. So they cancel out basically, right? And so they're catalyzing the reaction because they're not really included in the overall reaction. Like they're not affected by the reactions basically, so you can cancel them out. So yeah, it's true that they're catalysts. Like NO2 and NO are acting as catalysts. So statements 1, 2, and 3 are all right. Okay, and because of that, the answer is going to be A. So next question now. Question number 37. Which compounds contain a chiral center? 2-hydroxybutanoic acid. So let me just write out. So this is butanoic acid. Now this side will be my first carbon because the functional group side is the priority one, and then 2, 3, 4. So 2-hydroxybutanoic acid. So this is OH here, right? And does this have a chiral carbon? Let me see. Um, This carbon which I'm going to highlight right now, it does seem to be chiral to me because it has one OH, then this one CH2CH3 group attached, and this COOH group attached, and this one H atom as well, which you don't draw in the skeletal form, but yes. So 1 is right, it does have a chiral center, which I highlighted. Then 3-hydroxybutanoic acid, if I draw it out, it's like this. And 1, 2, 3, so it has an OH on this carbon. And if I highlight this carbon, it does seem to be chiral to me because it has one CH3 group and then one CH2COOH group, an OH group, and then one H group, which you don't draw in the skeletal formula. So again, 3-hydroxybutanoic acid does seem to be chiral. Then if I draw 4-hydroxybutanoic acid, this 4-hydroxybutanoic acid, so 1, 2, 3, 4. So on the fourth carbon we have OH. It does not seem to have any carbon, because if I look at this carbon, it has two atoms attached to it, right? So two identical groups attached, which means that it cannot be chiral, right? Because it has to four different groups attached. So this, and the other carbons are also not chiral. So it means that 3 is wrong. So 1 and 2 are right, which means the answer must be B. Okay. So yeah, next question. The diagram shows the monomer used to make polyvinyl chloride (PVC). Assuming that one particular molecule of the polymer forms from n molecules of the monomer, where n is many thousands, which statements are correct? The relative molecular mass of this polymer molecule is approximately 62.5 n. So let me find out what the mass of this monomer unit is. So I have two carbon atoms. So that means 12.0 times 2. And then 1, 2, 3, 3 hydrogen atoms, so 1.00 times 3. Then I have one chlorine atom, so plus 35.5, which makes it 24 plus 3 plus 35.5, which is going to be 62.5, right? So that's the mass of this one monomer unit. Now, obviously, if I have polymer, then it will be basically like n monomer units, right? So n of these monomer units, and because of that, my relative molecular mass will be approximately 62.5 times the number of monomer units I have, which is n. So 62.5, and that's right. So so not A, 1 is right. Now there are n chiral carbon atoms in this polymer molecule. So let me draw the, what do you call it, repeat unit. Right? It took me a long time to remember that it's called a repeat unit for some reason. Anyways, this is a repeat unit, right? Like if I have n of PVC and I have, poly PVC, right? Like this repeat unit of the, polymer repeated n times. Anyways, so let me see which atom here is chiral. I have, see this carbon atom. This one is not chiral because it has two H atoms attached to it, right? So it's not chiral, definitely. But the other carbon atom I have does seem to be chiral, because this carbon atom has this group attached, and on the other side it has another group attached, different one, and it has one H atom attached and one Cl attached. So it has four different groups attached with single bonds, and so it must be a chiral carbon atom. So I will mark it with an asterisk. And so since there, like for every one monomer, every one repeat unit of this polymer chain, I have one chiral carbon atom, and there are like n repeat units. So that means yes, I will have n chiral carbon atoms, because there are, yeah, you get that? I hope that makes sense. But yeah, 2 is right for that reason. And the next one is there are 5 n sigma bonds in one polymer molecule. So the problem is whether we need to count these two other ones or not. So what we can do is we can just draw a chain. So let me assume that I have one chain of two repeat units. Okay, that's my full chain. And just for safety, or like just to be sure, I will also make another chain. So I can make sure it's just not a one-off occurrence. This is one chain where I have two monomer, two repeat units, and then let me make another chain where I have three repeat units. Okay. So assume that one of my polymers has two repeat units, and like two of the repeat units. Like that's how long it is, and yeah, and stuff. Okay. So I will show you what I'm trying to say, because right now I'm just rambling on about random repeat units. Okay, but I will show you what I mean. Anyways, so in this first polymer that I have here, how many bonds do I have? Sigma bonds. So sigma bond, yeah, 1, 2, 3, 4, 5, 6. My pen is stuck. Okay, wait. 6 and 7, 8, 9, 10, 11. Okay, so I have 11 here. Okay, and in the other one, which I have three of the repeat units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, let me just count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so I seem to have 17 here and 11 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. So anyway, if it was 5n, that would mean that this would be 5 times 2, which is equals to 10, because I have two repeat units here. So I should have had 10 sigma bonds here, but I have 11. As is clear. So that means it's basically 5n plus 1 here. And then over here I have 17, which means it's 5n plus 2. So I'm not really sure what the trend is. Maybe I calculated it wrong, but Um, basically, otherwise this would be 5 times 3, which is 15. Okay, so it's not. These are 17 and 11, which is definitely not 10 or 15. So that means that this statement that there are 5 n sigma bonds in one polymer molecule is not right. So apparently the trend seems to be that over here you have 5n plus 1, then here you have 5n plus 2, then another one like where there are 4, you would have 5n plus 3. That's, I mean, I'm assuming that, but I'm not sure if that's actually the trend. Maybe I'm wrong. But maybe it's if I draw one with 4 carbon atoms, let me see, because maybe the trend is just 5n plus 2. So let me assume that I have 4 carbon atoms. Okay, I'm sorry, but let me check this. Okay, what is coming? What comes here? Yeah, okay. H H C L, right? So I had 11, and then now 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So 23, which means it's 5 fours are 20, and then 20 plus 3, so 5 and plus 3. So apparently it seems that like for when you had two carbon atoms, the number of sigma bonds was 5 and plus 1. When you had, sorry, not carbon atoms, I mean the repeat units. When you had 3 repeat units, it was 5 and plus 2. When you had 4 repeat units, it was 5 and plus 3, and so on. That's the trend I see. But if I'm wrong, again, you can tell me in the comments. But the point is, they're not just 5 and sigma bonds in one polymer molecule. Okay, so then 1 and 2 are the only ones that are correct, and because of that, the answer is going to be B. Okay. Now, next question, question number 39. An organic compound X has the following skeletal formula. Which statements about X are correct? X is a primary alcohol. That's right, because this carbon atom that the OH is attached to is only attached to one carbon atom directly, right? That means yes, it's a primary alcohol. X will dehydrate to give a single alkene. Okay, let's try this. So OH is here. Then the carbon atom that OH is attached to, the carbon that's atom that's adjacent to that, if we lose H from that, right, and we lose this OH, so what will we get? We will get this compound, right? So that's the only thing we would get. Like we are basically losing this OH and losing the H from here. So we get a double bond here, and we get this thing, right? So it's propene. If I'm not wrong, one, two, three. Wait, I think I'm wrong actually. But yes, you are. One, two, three. So one, two, three. And is there any other product formed? I named it wrong, but the product would be formed. I don't think so. That's the only product that could possibly be formed. I mean, the naming starts from the functional group, right? So it should be one, two, three. So this would actually be uh, 2-methyl prop. So, or I could just call it as methyl propene, I suppose, or maybe like I should say 2-methyl prop one in prop one in. I mean, is there any other propene version? No, methyl propene. I'll just call it. Okay. Anyways, if I'm wrong, again, tell me in the comments. But that's what I said. Anyways, X will dehydrate to give a single alkene. Yeah, so that's the single alkene, methyl propene, and then X will undergo a substitution reaction with chloride ions. I mean, yes, because there's that OH group, so it can undergo a substitution reaction with chloride ions, definitely. I would say that's right. If I had like DC5 or something, I suppose. So yeah, A is the correct answer here. And finally, the last question. 2,2,4-trimethylpentanal is used in the manufacture of adhesives. Which reagents would 2,2,4-trimethylpentanal react with? 2,4-DNPH reagent. Okay, so pentanal, that al at the end implies that it's an aldehyde. And aldehyde is a group which has carbonyl, right? So because it has carbon, and it's actually like this, right? Like that's the functional, sorry, the form, like the general form, like how aldehydes look like, and use RCHO. So, anyways, because it is a carbonyl, like it is a carbonyl because of the pentanal, it's an aldehyde, which means the carbonyl, carbonyl. Sorry, I don't know why I said carbonyl so many times. Carbonyl. So because of that, it will react with 2,4-DNPH because 2,4-DNPH is a test for carbonyls. And then Tolan's reagent, it would also react with Tolan's reagent because again, it's an aldehyde. Aldehydes give a positive result for Tolan's reagent. Like it's the silver mirror test, and silver mirror is formed when you use when you react Tolan's reagent with an aldehyde. Um, yeah, because Ag plus goes to Ag. And alkaline aqueous iodine. So for that, I'll draw out this molecule pentane now. And one, two, 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 and one, two, three, four, four, trimethyl pentanal. I suppose that's how it looks like. And so would it react with alkaline aqueous iodine? Well, alkaline aqueous iodine is the test for like methyl ketones or generally methyl ketones or secondary alcohols with adjacent methyl groups. But also it would give like a positive test for some other things, like for example, what do you call it? Ethanol. Like this is the only I think aldehyde which gives a test like CH3, CHO, and also I suppose with ethanol maybe just CH3. I'm not not ethanol, but this thing CH3, CH, OH because that would be a secondary alcohol. But like if I had R here, but instead of R, if I had H here, that's also one like that is actually ethanol, isn't it? Yeah, it is ethanol. I don't know why I was saying ethanol. Ethanol. Okay, so this is ethanol. And this is ethanol. So they also give a positive test for the alkaline aqueous iodine. Because basically alkaline aqueous iodine is a test for like the groups CH3CO, or for CH3 COH, which methyl ketones have, and also secondary alcohols with adjacent methyl groups have, and also ethanol and ethanol have. I'm not sure there are other things which also give positive test with alkaline aqueous iodine. If you know some of them, then you can write them in the comments. But those are the ones I know. And I don't know why I was so confused about ethanol. That's obviously ethanol, bro. But anyways, the thing is, this one does not have the CO is here. It does not. It's not a methyl ketone. It's definitely just an aldehyde, which is not ethanol, and it's not a secondary alcohol. It's just a methyl group either. I don't know why I went to such a long tangent. The point is that three is wrong. Okay, so only one and two are right, and because of that, B is the answer. Okay, that's it. So yeah, alkaline aqueous iodine does not give a positive test with this thing, and so B is the answer. And yeah, we are done with the paper. I hope you guys enjoyed. I think I just said a lot of random things today. So yeah, but hopefully, it was of benefit. Those random things were of benefit. So yeah, thank you for watching, and yeah, have a nice day.